have two questions on object-oriented programming. So here's a definition of a class. A class should always have at least one function, which initializes it. Yeah. And the initialization stage, you basically want to define the class variables. Okay, so when the object is instantiated, it should have some variables if you want to make it do something. So as it's instantiated, usually you have to provide some data to it, and the instance of it, which is an object, should be the same class with that given data. So this is the init function that should be in any object-oriented programming. But one thing that you have to understand is that when you define a function inside the class, the functions inside the class is called objects. So maybe I should write that down here. Typewriter. So here, no, not objects, sorry, methods. So anything that's a function inside a class are called methods. And methods are different from the class that it's always expected that the very first argument receives the function, the object itself. So here's what happens. So let me tell you the correct answer first. So this is the correct answer, B. And what really happens here is that once this is called, this is what's really happening is internally the employee, so E1 becomes the employee, one instance of the employee, and the employee dot init of E1 John 33 is actually called. So as you can see, the instantiated object gets plugged into a method. That's the difference between a method and a function. Okay, and therefore, even if you don't have the self in the first one, E1 automatically goes in there. Yeah. So that's one thing about object. And for the second one, sorry, I need to save this as a different name, or else it's going to overwrite it. Oh, made a mistake. Let's see. File, save as. Browse. Document. Okay. All right. So next. So here I have another class called car. Yeah, and then as you can see, this initialization function doesn't accept anything. So that's why when you see this right here, my car is an instance of the class car, but you didn't pass anything to it. So actually what happens here is that when it's executed, you see that the actual execution is car dot underscore init underscore my car. That's what's happening. So my car is passed on to it, and my car dot make now becomes Honda. My car dot model becomes Civic. My car dot year becomes 2021. Okay, that's what happens internally, right? So for example, in the next line, if I did what's my car dot make, it's going to answer Honda because I made it so. Okay. Now here I made another method called change model, whose role is to change the model, the civic, into something else, say a chord or something else. Okay. And the question says, suppose I want my car to be upgraded to CRV, which of the following would work? And there are multiple answers, and you have to choose all to get full credit. And if you only get partly right, then you get partial credit. Okay. So first of all, again, this is wrong. Oh. You should never pass the self to a method because that's automatically passed. Okay. So the correct way to do it would be to do this. Okay. If you execute this, then you ask what's my car dot model, then it's going to reply CRV now. Okay. Before executing this one, it will be civic. Okay. My suggestion is try to type these on a Google Colab or Jupyter, and you'll see what I mean. Okay. But then this is also correct as well. You can directly access mycar.model and change it to CRV. Okay. And D totally doesn't make any sense. Okay. So the answer is B and C. Now, you might ask, if you can do it like C, why make another function? Well, usually you don't want to make a new function like that. But a lot of people that come from purely like strictly object-oriented languages like Java, they tend to do this because usually in object-oriented languages, in other cases, it's not just for putting the data close together with the methods so it's easier to program and know what to do. Additionally, in languages like Java, you have something called a public variable and private variable, and these are made so that you can restrict other people from getting into a function, because if you program in a very big environment, having access to other people's other classes' internal variables that you're not in charge of debugging often leads to catastrophic results. So they're very strict about having a private variable, public variable, and stuff like that. And sometimes in Java, you would make a variable private, but you would allow that value to change to certain things by putting a setter. So there's something called a getter and a setter variable to allow you to access the private variables. Yeah, but in Python, it's really not needed. Okay. A digit classification data has 2000 bitmap PNG files of 8 by 8 pixel images. What is the number of features? I wonder how many of you can figure this out. So think of it like this. When you're presented with a bitmap file, what do you see in order to judge if this is a 1 or 2 or whatever letter it is? What do you see? Yeah?
Maybe like 3 features, right?
No. You see individual pixels to figure out if it's a 1 or 2 or something, right? But it's an 8 by 8 pixel images, right? So that means you have 8 times 8, which is equal to 64. There are 64 pixels per data. Okay. So in other words, you have 64 features per data. That's what it is. Okay. The answer is 64.
So it doesn't have to do with the size of the bitmap?
There are 2000 bitmap PNG files. Those are the size of the data. It's like the N. It's a sample size. It's a test size.
there's 64
features,
per-
yeah, per data, yeah, and you have 2,000 data points, yeah. In our data of what is it? Iris data. So do you remember what the features of iris data was?
pedal width,
Petal
pedal length,
width, petal length,
sepal width,
sepal width, sepal length. Okay. So how many features is that? 4. Okay. Yeah. But how many data points did we have? I don't remember exactly. Was it something like 90?
large amount.
Some large amount. I can't remember. Yeah. But each data point had 4 features, right? We had the measurement, the width and length of the petal and the sepal. And that's what was used to classify the kind of iris we had. Okay? All right, next. Which of the following is an example of a deterministic algorithm? Deterministic means that outcome does not change if it's run again. So neural networks, so anything that has to take the data set and you have to, let me see. Oh, okay. So for neural networks, what happens is that usually it starts by randomly assigning the weights. Okay, you put some random values for the weights, and then starting from that point, you do optimization of the loss function by gradient descent. That's how neural networks start. So that's definitely random. So in most cases, at the end of the day, you're going to get similar results. But if you run your neural network twice, you'll see that there are small differences. Yeah, not large enough, but it is definitely different. Random forest, of course, that's random, so it must be random. But random forest, what does it do? It first of all, it generates a random tree by randomly selecting a subset of the features. You don't use all the features, you just use subset of the features. And you also sample from the sample. So from your training set, you don't use all the training set, you just use like a sample of the training set to train it, okay? Which is called bootstrapping. K-means clustering, well, K-means clustering starts with some randomly chosen centroids and then you start expanding from there. So it's definitely random. But PCA is always same if you start with the same data set because it's just some singular value decomposition of the covariance matrix. That's why it computes, and there's no randomness involved in that computation. So PCA is a deterministic algorithm. In neural networks, which of the following is a strategy to find the optimal parameters to minimize the loss function? Which one is it?
D.
D. Yeah, you move in the negative gradient direction because gradient is the direction where the function increases the fastest, right? So if you always move in the negative gradient direction, then you're trying to find the minimum point. So, for example, if you're on a mountain and you want to go down to the valley in the fastest path possible, what you do is at every moment you just move in the negative gradient direction. Then you will be arriving at the minimum fastest. Okay, assuming that your movement is continuously determined. But in practice, what happens is that you always move by some learning rate, so it's a discrete movement, and therefore there's always a danger of going past the minimum point, and you may end up going in circles or stuff like that. That's why, in general, there are other more complicated ways which are you involve something called a momentum. You don't just always quickly change the direction to the negative gradient direction, but you add a small proportion of the previous movement, which is called the momentum. So in the TensorFlow demonstration I showed you, we used something called ADAM, and that was movement using some momentum. Okay, in neural networks, which one of the following is not a hyperparameter? So what's a hyperparameter? Hyperparameter is any of the parameters that's not trained while learning. So there are many many machine learning algorithms which requires training. For example, logistic regression requires training. What else? Support vector machines, they require training. You've run them, so you know, right? You run it and you have to wait a little bit until it sees all the data and figures out the optimal decision boundaries and stuff like that, right? And when it does those things, what it does is it tweaks its own parameters to find the optimal one that minimizes the loss function. But there are also parameters in the machine learning which are not decided during the training. It's decided before the training. So for example, in support vector machines, what kind of kernel are you going to use? That's going to be a hyperparameter because you have to set it before you run it, okay? So in neural networks, which one is not a hyperparameter? Would you have a guess?
Choice of loss function.
No, you have to choose it before running the training. So that's choice of loss function is a hyperparameter.
Oh, number of nodes.
You have to have it set before you train it. You have to fix the number of nodes. You also have to fix the batch size to train it. But once it's run, what does it modify? Weights are modified and also biases are modified, right? Sometimes biases are also called weights. So we just say weights in total. But weights and biases, those are tweaked until you find the optimal one, right? That's how neural network learns. So weights and biases are not a hyperparameter. Everything else are hyperparameters. And I haven't discussed this in class, but sometimes you have to figure out what's the best hyperparameter before you train. So what you do in that case is something called grid search. So grid search is like you come up with all the possible different combinations of the hyperparameters. Maybe you want the batch size to be 128, but then nodes to be 100, or vice versa. You have different combinations of those hyperparameters, and you don't train everything. You just train in a much smaller training set, and just compare them and see which one is best in the training. And once you do that, then you can kind of see which combination of the hyperparameters are the best, and then using that you run with the entire training set to train. So that's something that you would do. If this was a full-blown neural network class, then that would be definitely one of the things that I would teach, and plus all the other kinds of architectures like CNN and RNN, stuff like that. Okay. All right. When is the softmax activation function useful? What does the softmax activation function do? Do you remember? It's like e to the output of your own node. So let's say you're at node number I, right? But then you divide this by sum of all the values from the nodes. So you have e to the negative x1, right? And then plus e to the negative x2, and then dot, 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 until you reach the last output. So e to the negative xn. This is called softmax. Why would we want to do that? Here. I mean, taking exponential functions make the value to be positive, okay? The value becomes positive. Secondly, if you divide these values by the total sum, then after you get these values from each of the nodes, you add them all, then you end up having the total sum to be 1. In other words, if you apply the softmax to a output of a layer, what happens is that every value become between 0 to 1, and they add up to 1. Why would we want that? Because if we do that, then the output will have the meaning of probability. Okay? And you want to have the meaning of probability if your loss function is something like cross entropy, because they rely on assumption that the output from the previous layer is a probability. Okay? So that's the reason why softmax activation was used. And in our demonstration for the MNIST, we put it on the last layer right before the cross entropy so that your outputs can be interpreted like, this bitmap image that I just processed has the largest probability of being a 3 or 5 or something like that, okay? Yeah. And it was surprisingly useful, right? Okay. If the input layer has 21 input nodes and the next layer is a dense layer that has 30 nodes, what is the number of parameters in the dense layer? Okay. So let me ask, every node in this dense layer would have how many inputs going to it? Every node that will have how many inputs going to it? 21, right? So you'll have 21 inputs. So how many weights would be in here? Weights is the number that's multiplied to every input, right? So how many weights? 21, right? And how many biases? There's only one bias per node, right? So every node here would have how many parameters? 20? No, 21 weight plus one bias, 22 parameters per node, okay? So what's the answer here? 660, because you have 30 nodes, right? So if you recall, when we did the MNIST demonstration, there was something called model.summary. So we make the model as a sequential, we add the dense layer as one big hidden layer of 128 nodes, and then the last one we had added a dense layer of 10 because we wanted it to produce probabilities for each of the letters or the numbers 0 through 9. And if I did the model.summary, it's going to output at each layer how many parameters it has, okay? And if you do the similar computation, you can predict what the number of parameters are. And it's a good way to understand what's happening. If you can't make sense out of the model.summary, then you really don't know what's going on. If you can make sense of the model.summary by looking at the number of parameters and understanding what it means, then you have a better idea of what's going on. Yeah. Yes?
Can you just explain again? So you have 21 input nodes.
So every node in this dense layer, is going to receive 21 inputs, and every node itself has a bias, right? You know what these are? So maybe let me give you this idea. So phi is an activation function in the node, and what happens? A weight is multiplied to its input. So weight 1 is multiplied to input 1, right? And then plus weight 1, x1, and then plus until you get to weight 21, right? to be multiplied to the input 21. Okay, what do I put after this?
Plus B,
Plus B. What's B?
our bias.
Your bias. Yeah. It's plus B, which is the bias, and you enclose the parenthesis. Yeah. Okay, so that's one node. Okay, that's what goes on in one node. It calculates weight times the input, add them up, plus the bias, and you apply the activation function. Very simple. Okay, that happens in every node of the dense layer, and therefore, in our case, there will be 22 parameters to control, right? W1 through to W21, and B, that's 22. But that happens for every node in the dense layer, which is 30. So what's 30 times 22? 660. Okay. Okay, which of the following cannot be a loss function of a neural network? Here, y hat is the output of the neural network, and yi is the desired value of the output. Okay. So yi is the y training. Okay, y training. As you remember, the data set usually gets split into test and train. Training has x's, which are the features, and training also has y train, which are the desired output of the neural network, right? And how does neural network learn? Can we review that? Can anyone explain how neural networks learn? What does it do?
Take a lot of data.
It takes in a lot of data. It computes what? It computes the It computes the gradient. Why? What do you do with the gradient? Because gradient tells you which direction. Yeah.
You see where the errors are.
You're getting there, but before that, anyone else?
What's the minimum?
You're trying to go to the minimum, right? Negative gradient direction will point to the minimum of the loss function, right? So in other words, neural networks learn by minimizing the loss function. Loss functions have the property that if the target and the output are close together, the loss function goes to its minimum. It minimizes when the target and the outputs are close enough. And certainly you can see that in B, right? Right here, the desired output and the actual output are subtracted and you square this. This value is going to be getting smaller and smaller if they are close together, okay? So therefore, gradient descent will make it learn, okay? So that's good. Now, A, it's harder to see, but this is what's called the cross entropy. And this one does reach its minimum if yi and yi hat becomes close together, okay? So that's good. So that leaves us with C and D. Which one do you think is the answer? Which one cannot be a loss function?
Say D.
Wrong. It's C. It's C. Okay. D still. Do you know what cosine hyperbolic is? Maybe that's the problem.
Kind of.
Cosine hyperbolic is e to the x plus e to the negative x divided by 2. Okay? It's divided by, that's cosine hyperbolic. You learned this in Calc 2. But what's more important is that the graph is like that. It looks like a parabola, but it's not. This is what's called the catenoid, and it's the shape of the cable that's hanging when the two ends are fixed. So anyone's necklace, if you want to know what's the function that describes the necklace shape, it's the cosine hyperbolic. Yeah. One nice thing to try is to take a necklace, fix it on a piece of paper to two endpoints, right? And then just print a cosine hyperbolic function from any internet, and you can match it perfectly. Yeah, they hang in the same shape. Okay, so that's cosine hyperbolic. But here, what I'm trying to say is that when is this minimized? Cosine hyperbolic is minimized at 0. So for this to be minimized, what do you know? yi and yi hat must be same to be minimized. So that's perfectly fine. Okay, so any function. So there are like infinitely many possible loss functions you use. Of course, among them, a and b are the ones that are already defined and it makes the most sense. But you can certainly make your own loss function if you have different goals. I mean, you can also have like subtract the two things and take even powers. 4th power, 8th power, anything will be possible. It will still be a loss function because they'll be minimized when the output and the desired outputs are the same. But look here. This one doesn't have a minimum. Why? Because it only has a power of 1. So the output of this machine will be, the loss function can be minimized if the machine just puts out huge negative values, like negative a million, negative billion. It's going to make this more and more negative. So this function actually doesn't have a minimum. See, a line equation doesn't have a minimum, right? If you have a line equation, does it have a minimum? No, it can go down. Only when you have a parabola or something like that, if you have something like this, you have a minimum, okay? So C is not good. This cannot be used as a loss function for a neural network. Okay, which of the following activation function has a point which is not differentiable? When is a function not differentiable?
When it's not continuous.
That's one. But even if it's continuous, it can sometimes there is no derivative at what kind of points? Huh? When you have a sharp turn, okay? Yeah. When you have a sharp turn, it can't be differentiable at that point. A, RELU, right? Okay, so rectified linear unit, that's what RELU means. And it's like, it's a linear unit where it's chopped off, okay? So that's why it's called rectified linear unit. And there is a sharp turn, so it doesn't have a derivative there.
Can you show us the other functions?
Okay, yeah, tangent hyperbolic and sigmoid look the same, except that tangent hyperbolic goes between -1 and +1. So the minimum value is -1, +1 is the highest value.
What was the function for tangent hyperbolic?
It's can I write it? Let's see. Yeah, I'll just write it. So tan hyperbolic x is equal to exp of x minus exp of -x divided by exp of x plus exp of -x. Okay, so that's the function. You can basically take this formula on the right side and put into something like Desmos, and you can see that the graph goes between -1 to +1. Okay. Sigmoid goes between 0 to 1. Okay. We already discussed softmax. A random variable x has the following probabilities. What is the entropy of x? Okay. So how is the entropy defined? I said entropy is the expectation value of negative ln of p. Because negative ln of p, I explained in the class that negative ln of p basically gives you the information content in a probability. Now, one thing that is slightly different is in class, I actually used log base 2. And in information theory, they have different names. So log base 2, I forgot what it's called, but they're distinguished. But for the purpose of machine learning, in machine learning, we just use entropy to train the data. And whether you use ln or log base 2, it doesn't matter. You get the same result in the training. It gives you different values of entropy, but it gives you the same training. And therefore, and besides, it's easier for us to use ln if you're trying to calculate these with your calculator. So we'll always use ln. Although, if you look on Wikipedia or other sources, you will always see that it's supposed to be log base 2. And there's a rationale for it. We talked about using, Pokemon cards. You remember? Okay, well, that's what we did, okay? Yeah, but how do you find the expectation value? Expectation value is the sum of probability times whatever thing that you're trying to find the expectation of, right? So that's what it is. So which one follows this? Well, you can pull the minus out, right? So you can do, this should be equal to negative of sum of probability times ln of p. What's that? Which one is this?
It's B.
It's B, yes. Okay. Oh. Okay, 12, we have a typo. I forgot that some special characters in LaTeX. I made this in LaTeX, and some special characters in LaTeX, it will it's not rendered, so there's like a whole bunch of text that's gone. So let me skip 12 for now. I'll return to this on Tuesday. Okay. 13. Why does taking logs help in the naive Bayes classifier? So if you recall, how does naive Bayes classifier work? Basically, it says like, oh, if you see the word $1 million and inheritance in your email, that's a spam, right? Yeah. So there's like a million conditional with spam, dollar conditional with spam, and then what is it? The inheritance conditional with spam. Those become high values, right? And you multiply them to find the probability that you're going to see all those words in an email, right? So you keep multiplying probabilities to find the overall probability, and you compare it with the spam case and the ham case. And then if the conditional probability is higher in the ham case than the spam, then you say it's a ham. If the conditional probability is higher in the spam case rather than the ham, then you say it's a spam. So that's what you do. But the problem is that if you multiply many probabilities, what's going to happen? A lot of these probabilities are like 0.01, 0.02. If there are like 300 words in one email. Some are shorter, but some long emails have like 1,000 words. Now, imagine what's going to happen if you multiply 1,000 probabilities. That's something like 0.01. What are you going to get? You're going to get 0.0000000, so many zeros and then some numbers, okay? Now, can computers store those numbers? No. Yeah, computers have a limit to how little it can store. So for double precision, I think you can go even like 10 to the negative 100 or something. But given that it's easy to have the probabilities go even less than that, it's going to be a problem, okay? So how do you make it still work? How do you make the computer be able to handle very small numbers close to zero? What's the idea? It's right in front of you. You can read. You can read, right? What's the idea? You take the log. Yeah. If you take the log of 0.00001, you get -5. That's a big value. Computers have no problem in storing that value, right? Yeah. So even if you have like 10 to the -100, which at some point the double precision floating variable will have trouble storing it correctly. It will just say it's 0. You just try this, okay? Open up Spider and type 10 to the power of -200. See what it gives. It'll give you 0. Yeah. And that's bad because it has to be something non-zero if you want to compare the two probabilities, okay? So that's why the logarithm is used, and the answer is C, okay? Okay, which of the following is not an unsupervised machine learning algorithm? Okay, what is an unsupervised machine learning algorithm? Can you explain to me? Unsupervised just means not supervised, right? But of course, somebody has to run the machine learning, so of course somebody's doing the work. What do you mean unsupervised? You just run it and let it learn on its own, right? The big problem of machine learning is that in most cases it requires human to teach it. How do humans teach the machines? Do you know?
Feeding it data and
Telling it what it is, right? So you have to feed in. If you want the computer to recognize a bird, you have to feed in millions of bird images and say, this is a bird, that's also a bird. This is also a bird too, and you just keep telling it's a bird, and then you also feed in images of people and then cars and all that, and at some point after seeing all these labeled data, you can figure out which is which. It's basically what it's doing is it's doing a classification problem. It has like, say 10,000 different objects it can recognize, and when it sees an image, it classifies the image into one of those classes, right? That's how machine learning works, right? But then what is an unsupervised machine learning? Well, you have unlabeled data, right? So here's the problem. You can hire a bunch of people living in India and China because their labor costs are much cheaper than here, right? And then it's basically torture. Like you make them watch like 10,000 pictures of cats, and they have to label cat. Okay, but that's like inhumane. You don't want that to be all done by humans. So instead, how do you make it work? You first put it into unsupervised machine learning, which means the computer doesn't have the label, so it doesn't know what to call it. But definitely this bird-looking thing, it doesn't know it's a bird, but it definitely doesn't look like a cat, right? So it should be able to classify things. So what an unsupervised machine learning does is it takes in data and it splits into like, oh, these things look similar, so I'm going to group it together. These other things look similar, I'm going to group it together. So basically an unsupervised machine learning algorithm is a clustering algorithm. Well, there is something else in addition to it, which PCA is an example. But a lot of the clustering algorithms are algorithms that just cluster due to similarities. Then it's a lot easier for people to work because now you have 10,000 images and most of the images in this class are cats. So you just quickly type cat, or just make everything cat and then just look for a few things that was misclassified. There will be some bird pictures or car pictures there. Those you just label it differently. That reduces the amount of work that the human has to do by like 1/10 or something. So, or even smaller. So that's the power of the unsupervised machine learning algorithm. Okay, and
clustering, correct?
clustering. So anytime you have a clustering that's unsupervised. So K means clustering is unsupervised. DB scan is another way of clustering, so that's unsupervised, okay? PCA is a slightly different meaning of unsupervised. PCA just figures out the most important feature. It's a feature extraction or dimensionality reduction algorithm. What it does is, let's say you're using feature 1 through 10, or maybe the data has 1,000 features, which could be possible if you're working with images, right? Every pixel is a feature. Or every pixel could be 3 features because if it's a color picture, RGB channel, that would be 3 features. So you might as well have a data set where each data point has like 1,000 features. Now, trying to work with all of them is not so nice. So you want to reduce the dimensionality. You want to make only a few features. And the way PCA does it is it takes a linear combination of the values of the features and makes like a few, like 10 or 20 very small set of features that captures the most of the data. Yeah. It's a dimensionally reduction one. So and to do that, you're only working with X. You don't need the label. So what I'm trying to say is that any machine learning algorithm, if it does not need the labeled data, you call it an unsupervised learning algorithm. Okay, you get that? So PCA is an example of an unsupervised one, and C is the only one where you need the labeled one. So you remember when we did the support vector machine classifier for digit recognition, and what was it doing? We had to give it labeled data. We had to feed multiples of images with this is a 0, this is a 1, and we had to give the machine several examples of it, right? So C is an example of a supervised learning machine learning algorithm. Okay. 15. Which of the following is not true about k-means clustering and db-scan clustering? Okay. K-means requires the number of clusters to be predefined, whereas db-scan does not. Okay. Yeah. So for this, here's my suggestion. Just Google difference between or comparison between k-means clustering and db-scan. They have their own merits or shortfalls. So just read upon the different ways that these two algorithms work and try to compare them. And let's see. K-means requires the number of clusters to be predefined. Yes. db-scan does not. Yes. So db-scan actually you have to provide the radius and minimal points number, and if it gets provided those two numbers, it will automatically decide on the number of clusters. So A is correct. Assuming hyperparameters are fixed, k-means clustering may give different results each time it is executed, while db-scan always gives the same result. Oh, this is not true. See, both of them are not deterministic algorithms. Both start by, k-means starts by choosing some arbitrary centroids and then it starts changing them. db-scan also starts by choosing random points in the beginning. Okay. db-scan requires radius and minimum points. Correct. So you have to provide the r value and the m value for it to begin. K-means you have to provide the k value, which is the number of points in the neighbor. K-means clustering does not work well with outliers and noisy data sets, whereas db-scan efficiently handles them. That's correct. That's the reason why db-scan was developed. Okay, in the db-scan algorithm, for given minimum points m and r, if a point has at least m points within distance r from itself, such a point is called a core point. So db-scan works by identifying, for each point, it counts the number of neighbors inside a radius r. If you have sufficiently many points that's above this number m, then you call that a core point. And basically the algorithm is you start like drawing core points, putting the radius r, and then putting another core point and a core point, and then the core points get connected by these radius r circles, and eventually they form one cluster. But then if some points are further away than being connected by core points, that becomes another group. That's how the clustering algorithm for DB-scan works, okay? So that's, core point is that a noise point is like, this algorithm allows for points which is not a part of any cluster. Those are called noise. And border points are points which are in a cluster but not a core point. Those are called border points because they tend to be at the border of each class. Outlier is a terminology for describing data in general. It's not one of the things inside the DB-scan. So really you have to know the terminology of the noise point, core point, and border point when you talk about DB-scan. What are some strategies in finding optimum value of k, and k means clustering? Yeah, multiple answers. So the thing is, when you do this unsupervised learning, you really don't, especially when you don't know the label. So we were doing k-means to iris data, which was already labeled. So we kind of knew what the desired outcome should be. But in many cases, when you're doing unsupervised learning, you don't really have a good idea of what k should be. So there are two ways to find the best value for k. And one is to find the k value which minimizes the silhouette score. Okay. Oh, it's just what is the silhouette score? 1 minus AI over BI. That's called a silhouette score, where AI is the average distance within the cluster to a given point. BI is a average score between the point. So let's say you have something like this. You have one group here and another group here. So you have two classes. Then if you pick this point right here, there's a silhouette score you can compute for this point, which is you take this distance, you take this distance, you take the average value. That's your AI, okay? You take this distance, this distance, this distance. That's your average value for BI. Okay? You take the average and that's the value for BI. Now, if this really is clustered, you would expect that the BI is much bigger than AI, don't you think? Right? Yeah. There are cases, although AI sometimes does become bigger than BI, that's not good. Yes?
Wait, you said BI is the average distance between the x points? Or
No. So if you pick this point, let's say we pick this point, okay? Then BI is the distance between this point and items in the other class. So you take this distance, this distance, this distance, okay? Take the average of those distances. And if it's really clustered well, you really want the BI to be bigger than AI, right? So the ideal case will be BI is much bigger. And overall silhouette score is you compute this for every point in your clustering, and then you take the average, okay? So so you want this to be large and this to be small so that this value will be close to 1. Oh, so in that case it will be maximized. Okay, so the answer is maximized, sorry. So we want to find k value which will maximize the silhouette score. Another way to do this would be you look at the graph of k values and what's called the within some cluster squared sum. And the more clusters you have, the sum of squares of the distances within a cluster will be getting smaller and smaller because your clusters become smaller, right? So the graph always goes like this. So graph always goes down like that. And when you draw this graph, at some point you see an elbow. It's also called a knee. And it means that the slopes are rather going down steeply, but at some point it doesn't go down that fast. So there's this elbow. And that point is also something that you think of as k. And in both cases, these are really heuristic. You don't know whether this is really the right one, but this is the best guess, okay? All right, that's all for today.